So we're going to look at how to solve systems of linear equations. Again, a system of linear equations is simply a fancy way of saying two or more linear equations that we want to find where they intersect. Remember, a linear equation is an equation that describes a line on the graph. So each of these equations I have here is represented by a line on the graph here. So if I draw a quick graph, this might be one of the lines, this might be the other line, and this right here, this point where they cross, that is the solution. That is the point we are trying to find. Now, if we could graph both lines, we can just figure out where that is just by looking at the graph. The problem with that is that it's time consuming, and sometimes the point isn't exactly on a clear spot, so it's kind of hard to see where they actually intersect, especially if your answer is a decimal or a fraction. So we mainly have two processes of solving linear equation systems. The first is substitution, and the second is elimination. I'm going to be using elimination because that is the process I have found people have the most success with on average. We may go over substitution later on, but elimination is the most successful way people have done these when I've taught them. So I'm going to stick with that method just so we can focus on one method and get good at that method before we try another one. And so there's three different types of problems you'll see in systems. The first one is the easiest type, which is this one here, which is kind of already set up for you. So we have 2x plus y equals 11, 4x minus y equals 7. The goal of elimination is to reduce it from a two-variable problem to a one-variable problem, because we cannot solve an equation if there's two unknowns in there, if there's two variables. We just can't do it. There's no way to isolate a variable away from any other variable, and there's no way to get it to be a solid number. We could rearrange it so that y is by itself or that x is by itself, but we couldn't get a single number as an answer. So we need to get rid of one of these variables, which is where elimination comes in. Elimination is the process of destroying one of the variables or eliminating one of the variables so that you're only working with one at a time. And it does that through either addition or subtraction. I'm going to focus on addition because subtraction has the properties of negatives, which can make it a little bit messy. So what we do is we simply add these two equations together, just like we would a pair of big numbers. We're going to add the columns. 2x plus x, that's 6x. Plus y and minus y, or plus 1y and minus 1y, when you add them together, they cancel, which is good. The point of elimination, as I said, is to get one of the variables to cancel or eliminate. So if you don't have one of the variables canceling or eliminating, then you can't do elimination correctly, which means you have to alter a little bit, and we'll get to those later. Bring down my equals. I even add the ones that are on the other side too. So 11 plus 7, that's an 18. And then I think to myself, how can I solve this equation? Something I've seen before. All I do is divide by 6, and I get x equals 3. Nothing too bad there, right? But I'm not done, because as I said, this is a point on the graph. So every x coordinate needs a y coordinate pair to get an actual point. So I have to figure out what's the y that pairs with this x. And the way I do that is I go back to my original two equations, I pick one to replace x in for, and I solve it for the remaining variable y. So first off, let's just pick an equation before we get to the hard stuff. I'm going to pick the top one because it looks the easiest to use, smallest numbers, at least on the x's. So I'll pick that one. 2x plus y equals 11. Now, I know that x is 3. That's why I solve for right here. X is 3. So why did I write an x again? I already know that x is 3. Why do I have a 2x here? Why am I saying 2 times x if I know that x is 3? So I'm going to rewrite this and say 2 times 3. Because as I said right here, I know that x is 3, so I don't need to write x anymore. I know what it is. I can just replace it with a 3. Everything else stays the same. Now I can just solve this equation like I would a normal linear equation. 2 times 3, that's 6. Minus 6, minus 6, get y equals 5. So my answer would be the point 3, 5. That is the point where these two lines cross on the graph. So again, you need to get both an x and a y point to solve the system accurately, not just one or the other. And the way we did that is that we add them together so that one of the variables eliminates or gets canceled out, and that way we can work with just what's remaining. If you want to check your answer, you can plug in 3 and 5 for the x and the y into the original equations and see if you get a true statement. So for example, 2 times 3 is 6. 6 plus 5 is indeed 11, so that one works. 4 times 3 is 12. 12 minus 5 is indeed 7, so that also works. So that's a way you can check your work to make sure you're getting the right answer. Now this, as I said, is the easiest one because it's already set up for you. There are ones more common that are not set up for you. Let's take a look at one of those. So this one here, if I try to do elimination right away, I come across a little problem. Let's take a look at what happens. Let's say I go about my business. I'm adding them together. 3 and x, so 3 plus x, that's 4x. Negative 2 plus 3, that's just 1y. Negative 8 plus 1, that's negative 7. Well, this is a problem, because the goal in elimination, remember, is to eliminate one of the variables. That's why it's called elimination. But I still have both of them in my answer here. I can't really solve for x or y still because they're both in the way. So I have to do some housekeeping first. So let me erase this here, go back to what we started with. So if that doesn't work, I'm going to look at my problem and say, okay, is there a way I can alter one of the variables, either one or both of the equations, so that when I add them together, it would cancel with the other? And remember, if you're changing an equation, as long as you do the same thing to both sides of the equation, that is a valid move. That's a valid adjustment. So if I take an equation and I add 5 to both sides, that does not change the value of the equation. It just changes the looks and the composition of it. Or if I take an equation and I multiply both sides by a number like 2, as long as I multiply both sides by 2, that's still valid. The equation hasn't changed. It just looks different, which in some cases is more helpful. So I'm going to look at this setup here. I'm going to say, well, this x and this 3x, and this 1x, those are pretty close to being cancelable. If that bottom x was a negative 3x rather than just a 1x, then I can go ahead and eliminate them because they would cancel. 3x and negative 3x would make 0. But it's not. So how do I change an x to be a negative 3x? Well, I multiply by negative 3 because negative 3 times x is negative 3x. So that's exactly what I do. I multiply the bottom equation by negative 3. Now remember, when I multiply by negative 3, I'm going to multiply every part of the equation by negative 3. Because as I said before, you have to do it to all pieces of the equation, to both sides of the equation, in order to keep it valid. Otherwise, you change the equation, and you're no longer doing the same problem. So let's see what happens here. I get negative 3x, negative 9y, positive 3 times negative 3 is negative 9, and negative 3. 1 times negative 3 is negative 3. On the top, it hasn't changed, so I'm just going to rewrite it as it was. Now, I'm going to go ahead and add these together and see what I get. The first x is canceled. That's good. That's the problem I had before, is I didn't have a variable canceling, and now I do, so I'm on the right track. Negative 2 plus negative 9 is negative 11y. Negative 8 plus negative 3 is also negative 11. So divide both sides by negative 11, and you get y equals 1. Wasn't too painful there. But again, I'm not done yet because I need to find the x that pairs with that. So I'm going to go to my original equations, figure out which equation I want to work with, and plug in the y of 4. The bottom one looks a little promising because it doesn't have anything with the x, so I'm going to choose that one. So x plus 3y equals 1. But again, I don't have to write y anymore. I already know what y is. I solved for it over here. Y is 1. So instead of writing 3 times y, I'm going to say 3 times 1, because I already know what y is. That's the whole point of what I did before, is so that I can figure one of them out. Now it's just solving an equation. X plus 3 equals 1, minus 3, x equals negative 2. So my final answer, all in all, will be negative 2, comma 1. So in this case, it wasn't set up for me right away, but I just had to make a minor change on one of the equations That way, when I add them together, everything fell into place. So sometimes you will have to alter one of the equations through multiplication on both sides of it so that it cancels with the other. Now, the third type of problem is one where it's all messed up, where nothing is given to you. Here, we just had to change one. Sometimes, like in this problem, you have to change both. So 2x minus 3y equals negative 10. 3x plus 4y equals 36. Again, if we just add them as they are, so if I add them as they are, I get 5x plus y equals 26. I still have both my x and my y, so I can't solve for either, so I have to do my housekeeping first. The problem with this one is that neither the x's nor the y's are close to being cancelable. I can't really multiply 2 by anything to get a 3, or anything reasonable. I could multiply by a fraction, but then it gets a little messy. Nor can I multiply 3 anything to get 2, or 3 anything to get 4, or 4 anything to get negative 3. So I can't really multiply just one, so I choose to multiply them both. What that means you do here is you pick a variable you want to get rid of. It does not matter which one. You can pick the one that looks the easiest. In this case, I would pick the y. So I'm going to mark over here that y. That is the variable I'm going to target for cancellation or for elimination. Why did I choose y? Well, again, I could just choose either one I wanted, but I saw that there's a negative y on top and a positive y on bottom. So if one y is already negative and one y is already positive, that's less work I have to do. I no longer have to make them into a negative and positive. They're already that for me. I can just focus on getting the numbers to be opposites. So I'm going to look at my y's. One's a negative 3, one's a positive 4. What's a common number I can turn 3 and 4 into? Well, we run through the list here. 3 times 2, that's 6. Can't make a 4 into a 6. 3 times 3, that's 9. No, can't make a 4 into a 9. 3 times 4, that's 12. Well, now that one will work, because what I can do is I can take this bottom equation and multiply it by 3. That way this 4 becomes a 12. I can take the top equation and multiply it by 4. That way this negative 3 becomes a negative 12. And that's what I want. I want one of the y's to be a positive 12, one of the y's to be a negative 12. That way when I add them together, they make a 0. Now remember, this goes to every piece of the bottom, and this goes to every piece of the top. So let's rewrite how these would both look. We'll do the top one first. So 2 times 4, that's going to be an 8x. Negative 3 times 4, that's negative 12, which is what I wanted. Negative 10 times 4 is negative 40. Now we do the bottom. 3 times 3, that's going to be a 9x. 4 times 3, that's a positive 12y, again, what I wanted. And then 3 times 36, that's going to be 108. So now comes the part where I add them together. And as I said, if I did this correctly, my y's should make a 0, because it's the one I wanted to cancel. Well, the x's make 17. Negative 12 plus positive 12 does indeed make a 0y, so these cancel. And that is good, because now I just have one variable to worry about. The other part here, 108 plus negative 40, would get me a 68. Then, now that I'm down to a single equation, I can go ahead and divide both sides by 17. And I get x equals a 4. But, as I said before, not done yet, because we need to get that y pair that goes along with this x number here. So the rest of this is the exact same as we did before. You pick an equation, you replace the x with what you solve for it, and you get your missing value. In this case, I would choose the bottom equation, because even though it has bigger numbers, the top equation has a negative 3y, and I'd rather not deal with the negative. Even though it's a pretty easy negative to deal with, I'm going to choose this one because it has no negatives. So 3x plus 4y equals 36. But again, I don't need to say 3x anymore, because I know that x is 4. I solved for it over here. That's the whole reason why I did the elimination. So instead of saying 3 times x, I'm going to say 3 times 4 plus 4y equals 36. Drop my line down the middle just to help me out with my sides. 3 times 4 is 12, plus 4y equals 36. Subtract the 12 to get rid of that first. Get 4y equals 24. Then we divide by the 4, and we get y equals 6. So that's my y pair. So my answer altogether would be the 0.4, comma 6. And that's the point where these lines cross. Again, if you want to check it, plug in 4 and 6 to the original two equations, and you'll be good. Now, when I was plugging my x, I could technically choose from any of the 4 equations I have. I could plug the x into this one, to this one, to this one, or to this one. It does not matter which one I choose, but usually the beginning equations are the easier ones to deal with because they have the lowest numbers. But again, it's up to your choice which one you want to use. Now, word problems for systems can get a little tricky because usually they give you a lot of information because they have to. But as long as you keep your information organized in the problem, it shouldn't be that big of a deal. Let's take a look at one here. So we have 3 friends going to see a movie. They buy 3 tickets, obviously, and 2 bags of popcorn. They spend $25. A married couple, so again, we're assuming 2 people, goes to see the same movie. They buy 2 tickets and 1 bag of popcorn, and they pay $14. We want to figure out how much is a movie ticket and how much is a bag of popcorn. Not together, but separately. So this is actually a systems problem, even though it might not look like it at first. So we have 2 types of unknowns here, right? We have tickets and we have popcorn, the cost of each. So we're going to have to identify 2 variables. You can use x and y if you want. I prefer to use variables that remind me of what I'm looking at, so I would do t. Actually, let me do k for tickets because t kind of looks like a plus sign, so k for tickets. And I'll use p for popcorn. And remember, this is not the number of tickets or the number of bags of popcorn. This is the cost. So it's the cost of a ticket and the cost of a popcorn. Because we're not looking for how many popcorns they bought. We already know that. We want to look for how much did it cost for just one. So now that we have this, we can actually set up a system. We can say that 3 tickets plus 2 popcorns cost $25. And 2 tickets plus 1 popcorn costs $14. We want to figure out how much each variable is on its own, so we can solve for the solution of the system. Let me give myself some space here. And we'll see what type of problem this is. So is this a problem that's already set up for us? Is this a problem we have to alter one of the equations in, or is it a problem we have to alter both in? Well, if we take a look at it here, the p's are the ones that immediately stand out to me because they are pretty close to being cancelable. I have a 1p down here and a 2p up top, so they're pretty darn close. But I might need to change the bottom one a little bit. So if I could change the bottom p to be a negative 2p, that would be a lot more beneficial for me because then they would cancel. So let's go ahead and do that. How do I do that? Well, I'm going to multiply the entire bottom equation by a negative 2. Notice I'm doing negative 2, not positive 2, because I want to cancel with the positive 2. I can't cancel a positive 2 with another positive 2. I have to do the opposite. So my top equation is going to be the same. 3k plus 2p equals 25. Bottom equation would be negative 4k minus 2p equals negative 28. Again, just multiply the entire bottom equation by 2 to get that result. Okay. Now is the time where I add them together and actually do my elimination. So I'm going to add these together. This would get me a negative 1k, or just a negative k. The p's would go away. That's what I wanted to begin with. And 25 plus negative 28 would give me a negative 3. Now you can think about this one of 2 ways. If negative k is negative 3, that means positive k has to be positive 3. Because I want the positive version of the variable, not the negative. Because I want to know how much 1 bag of popcorn costs, not how much negative 1 bag of popcorn costs, if that was even possible. If you don't like this way, you can also just divide by negative 1, because that's technically what's in front of the k is a negative 1, because 3 plus negative 4 is negative 1. We just normally don't write the negative 1, we just write the negative, but it is still there. So far we found that tickets, I said popcorn in the past, I'm sorry, but it's tickets. So far we found that tickets cost $3 each. Okay. Well, that's half our problem. We need to figure out how much the popcorn costs now. So which equation looks the easiest to use? I'm going to use the bottom one because it has the smallest numbers and probably the easiest one to take care of. So I'm going to rewrite my bottom equation. 2k plus p equals 14. I'm going to put a 3 in for k because that's what k is 3. Whoops, I wrote my 3 backwards there. I'm sorry. Let me do this correctly this time. Plus p equals 14. Then I go through my linear equation steps. So 2 times 3 is 6. Subtract 6, and we get p equals 8. So the point on the graph would be 3, 8, but I'm not really looking to graph this. I'm just looking for what the answer to the question is. How much is one ticket? How much is one popcorn? So my answer would be one ticket is $3, and one popcorn is $8. So what we learned through the problem here is that you are getting very ripped off by buying a bad popcorn at the movies. Now, mathematically, what we learned here is that in this case, we could set up a word problem to be representative of the system if we have two unknowns that we're working with. So if I have a problem where there's two things I'm trying to figure out, like say the speed in the miles, or in this case, the cost of tickets or the cost of popcorns, or another popular one is adult tickets sold versus children tickets sold at a concert or a fair or something like that. If we have those types of problems where there's two unknowns, then we can set up a system for them usually, use elimination, solve for them each, and get our answer that way. So if you have two unknowns, try to set up as a system if you can. Hope you enjoyed the video. Have a good day.